Well, it's just as Eric Dollard says it is, contrary to my desire to um, find a way around Eric Dollard's admonition that you can't synthesize electricity in amounts smaller than 500 kVA. Despite my attempt to want to get around that, it's I wasn't exactly successful. In fact, all I could do was produce 4 megawatts of power, 4 negative megawatts. Negative as in this thing is not a motor anymore. It's now a generator. Um, Now, the whole point to this exercise was to see if I can get it to motorize, to self-turn, and produce its own power at the same time. And I always envisioned this possibility when I bought my electric car back in 2013, that the motor could become a generator. Of course, I didn't realize I might have to rebuild the motor from scratch or major modifications to an off-the-shelf AC motor. I don't know. Single-phase AC motor. I don't know how to deal with three-phase AC motors, so I won't even go there. But little in my wildest dreams would I consider the possibility that there's no way to produce this free energy in small amounts. And if you consider 4 megawatts, that's a lot of energy. That's comparable to San Onofre nuclear power plant when it used to be in operation. It's also comparable to lightning. It's a humongous amount of energy. But the Edwin Gray team of Richard Hackenberger, physicist, or electrical engineer, I should say, did figure out what to do. Now, initially, they had no clue. Now, let me go through some of these schematics. So this is a composition that you can download at is.gd/Heaviside Ferranti. I misspelled it originally, F-A-R-R, but it's F-E-R-R-A-N-T-I, Ferranti. Now, Ferranti, apparently a lot of people were making the mistake, the same mistake. Ferranti wasn't the only one. There was a guy in America who was making the same mistake, and the Royal Society of London. So 3 different groups of individuals making the same mistake, thinking, oh, this transatlantic cable problem we're having, they didn't have any repeaters, any boosting stations in the Atlantic to boost the signal like they did on land when they had the telegraph operation in the 1850s. They had earth batteries every 150 miles or so to boost the signal. They didn't know what they were doing. They just, oh, it works, so let's do it, And they found if they extended the distance between the boosting stations, they actually started to get a little over unity. But in the Atlantic Ocean, they didn't have that advantage, What is it, 1,000 miles or more or something, And the only thing that got across was the electrostatic component, the electric field. Eric Dollard has said, nothing transmits through the wire anyway. It happens in the wire as a, what did he call it, a blending or a place of junction, a meeting ground between the 2 fields that surround the wire. But it's the electric field and the magnetic field that propagates down the outside of the wire, where the space surrounding and inside the wire, it's the space. It's the wire is just in space, in empty space. There's no waveguide, no wire to act as a waveguide to serve as the junction point between the 2 fields, and so we don't see electricity in space. We just see a lot of dissipation of magnetism very quickly, because electromagnetic waves do not travel through space. They get dampened down by space very quickly because they're a short-range influence. It's only the electrostatic that traverses an infinite distance because it doesn't travel. It induces it. The effect of a voltage change in one area of the universe affects all areas of the universe simultaneously, because it does not travel. It doesn't have to travel. But electrostatics can't. That's why it's called static for a reason. It ain't traveling. It ain't moving. Yet its influence is immediate. It's instantaneous because it doesn't have to move to create a reaction, a voltage reaction, everywhere else in the universe. So everything in the universe is instantaneously connected via the dielectric medium of empty space, the vacuum of empty space. So it's a figure of speech to say energy from the vacuum, because you're not getting energy from the vacuum. It doesn't happen. You're getting it from time, but that's not the purpose of this video. Anywho, so here is the composition, and we have an insert of the schematic. We have an insert of the input to compare with the output of wattage. Then we have the output in terms of volts RMS, 3.4 kilovolts, and 1.95 kiloamps RMS. And then we have, that comes from this diagram here, the separation between the RMS amps and the RMS volts. But that's the insert, and here's the link. So now let's look at another schematic if we can find it. There we go. So this is the full schematic. And so what I did was I took my old model, which is totally voltage oriented, and I inserted a transformer in here. And I connected it via another little rotor coil to make the first rotor coil bifilar. So now they're entwined together in the rotor. And how are we going to fit a transformer inside the rotor that has 10 henries on one side, on the secondary side of all places, and 200 nanohenries on the primary side, so it's a step-up transformer? I don't know. But in any case, I measured the energy of the first rotor, the primary rotor, and the secondary rotor together to give us this combined effect. And then, to contrast the output, I measured the input at the sine wave generator. Now normally without this transformer inserted in the circuit, the current input is noise. It's random activity, and only the voltage input is a nice clean-cut 3-volt sine wave at whatever frequency. In this case, I was able to lower the frequency to 20 hertz. Normally, I don't get to do that. Maybe I might go as low as 30 plus a little. But normally, I like to hang around between 50 and 70. And the simulator, unfortunately, has a limitation. It cannot go above 1.35 megahertz. So it's not to say you cannot go any higher. I think it's really a problem of the simulator. Simulators all have their limitations, and you have to work within those limitations. And computers have their limitations. So between the limitations of the computer and the simulator, I have my limitations on what I can do. And because I bought this, well, I didn't pay for this simulator, microcap simulator from SpectrumSoft. I'm using their free demo version from 2017, version 11. I don't get to do much. I have to keep everything simple. And so you don't see me putting in starter coils here. And I renamed what used to be the starter coils my current coils, because that's what they are. They have 0 voltage and nothing but high current. And then the voltage coils have lots of voltage and only a minuscule amount of current. So I named them VC for voltage currents, voltage coils, I should say. But this is the electrostatic area of the circuit, all of this. And then this is the electromagnetic portion. Okay, so it's 2 different portions lumped with all these different lumping relationships, except for here is the only area that is not lumped. It's an actual true transformer representing the motor armature of the single-phase induction motor. Because this is all AC. But the starter coils have to be well, they have to be DC because everything here is negative power factor, in which the current and the voltage are out of phase by a whole half cycle, 180 degrees. And I doubt this thing will rotate without the help of either starter coils converted into DC or a little electric motor. See, I forgot about that. I better add that in my chapter on rotation challenges. A little electric starter motor to get this thing started, and then the electric starter motor can disengage once this thing starts to turn. Now, when you want to go in reverse, then you have to put it in, you have to come to a stop, hopefully, and then the little starter motor has to start again, but in reverse direction to get you to go in reverse. But this thing won't start to turn. There's no way it's going to happen. Now, there is a chapter, I think, in my book somewhere, in which I talk about reverse winding, because you have to accommodate the fact that the current and the voltage are out of phase. And that'll work for these coils to do reverse winding. But what about these coils? You can't. If reverse winding is not going to help. Well, let's see. No, maybe it will. Oh, maybe it will. I didn't do that in my simulation. I'm going to have to do that. I didn't notice any difference in power gain, so I didn't bother to do it, but I forgot. You're supposed to do that. Because one side, the top side here, is 200 nanohenries, and the bottom side here is 10 henries. That means all your current is going to be congregating over here in the 200 nanohenry coil, what I'm considering the primary coil. And then the secondary, the 10 henry coil, is going to be where all your voltage is going to hang out at. So if you cross-wind them, you'll be able to put the negative power factor back in alignment with itself so that its positive power factor, I'm assuming, I'm speculating here. There's no way for the simulator to tell me this. Well, it should. Oh, let's see. Now that, according to Microcap help file, the way you do it, they don't allow you to swap the terminals like Paul Falstad does in his. Here they say you have to make the coupling coefficient negative. So let's make it negative. And now let's simulate. So what will we be looking for? Let's see. We'll be looking for at least this coil. It should show up on the other rotor coil. The voltage versus the amps. So we won't do RMS. Of course, that'll obliterate the waveforms. Oh shoot! I didn't shrink down the. Whoops! Sorry. 80. That's a little high. Huh. Sorry. All right, let's start that again. Let's get rid of that. Okay. Oh shoot! Now it's not going to work. Okay. Sorry, a little technical glitch here. Now it'll work. There we go. Let's see. So why don't I give you the rest of the lecture while we wait for this to simulate. So Richard Hackenberger had a problem. The EV Gray motor could not produce small quantities of energy because it was correctly designed for speed, to provide speed in an electric vehicle, unlike the Joseph Newman motor, which cannot because there is no iron armature. All it can do is give you torque at a very slow speed. Not unlike the DC motors taken out of forklifts in the early days of electric vehicle conversion kits and, tinkerers in their garage. Oh, that was quick. Let's see. So now we got to get the voltage. See? Look at all those nice 1.6 kilovolt spikes. 1.511 kilovolt spikes. Very fast frequency, so that'll have a good gripping action between the rotor and the stator. Let's see. Oh, and by the way, that's what I'm See, I'm assuming here that one of these coils on the transformer is the rotor, I guess the 200 nanohenry, and then the stator would be the 10 henry. But the input side, the primary side, is the 200 nanohenry in terms of the wiring. So let's get the amperage for this. Let's see, I, rotor 2. Normally you would combine them, but I just want to look at the waveforms. Oh, they're huge. I should have done that first. Yeah. Well, let's see. We can increase the size of this. We'll have to. Oh, shit. Sorry. Let's start again. Excuse my French. Or my German, if you prefer. Why is it taking so long? Oh, shit. I got to go all over again. Okay, so the Richard Hackenberger team had a problem. What to do with all the excess energy? And in the beginning, all they could think of doing was to throw all that excess energy into a bunch of batteries. So they had 2 batteries to power the motor, and then they had 2 batteries to dump the excess energy in. And they were blowing up the lead-acid batteries. They didn't know what to do. And then the FCC came in and raided them because they didn't have an AM radio on nearby to let them know of all the electrostatics and electromagnetic noise that they were broadcasting in their local neighborhood. So they were raided. So let me finish my thought before So what Richard Hackenberger did was he came up with a solution. What he did was he got rid of the batteries. Obviously, they weren't doing the job. And he forced compressed air through the interior of the motor to blow out the first of all, to prevent arcing and to blow out the ionized air so that the fresh air coming in could get charged up and carry the electrostatic charge of the motor away from the motor. And then the ionized air could ground itself to nearby objects and everybody would be happy. Hopefully, it would not be positive ions because that creates smog. Hopefully it would be negative ions and help create rain and clear out the smog. But be that as it may, it could be a mix of both. It could be a random mix of negative and positive ions. We don't know because Richard Hackenberger didn't do an EPA. See, now, if he wanted to comply with the EPA, he would have had to figure that out and get it to be either balanced or negative, because if he was producing positive ions, that would be unhealthy for plants and animals and humans. Anywho, be that as it may, they weren't thinking ahead. They were just trying to get the thing to run and get investors and get money. That's all Edwin Gray wanted, was money to flow in. But they had problems at times towards the end with money. And Richard Hackenberger dying of a heart attack because it was very hard to live with Edwin Gray. Anywho, be that as it may. Or work with him. So then what he had to do, though, is he had to build up the electrostatic field surrounding the motor. He had to convert all that excess energy that the motor was not using into electrostatics. And to do that, he had to make a few modifications to the prior developmental stages of the Edwin Gray motor. What he had to do was, besides blowing compressed air through the motor, that was the first step. The second thing he had to do, and you'll see this in the patent if you look up the patent of the Edwin Gray motor, he had brackets, aluminum brackets, supporting the coils, because this was a pulsed DC motor, and the coils were, it's not like an AC where you've got, well, whatever. AC is a little different. So a DC pulse motor, he had aluminum brackets, and they were insulated from the interior other parts of the motor. So the aluminum brackets supporting the coils inside the motor, they were electrically isolated so that they could build up an electrostatic charge. Now the coils themselves will also have, or I should say the coils, but most particularly their insulation of the wire, will also build up an electrostatic charge. And this is important. I never realized this till just this morning when I gave it some thought. Now on the outside of the motor, he put 9 bands of copper, sheet metal, around the circumference of the motor. So, most motors are barrel-shaped. or drum-shaped. And so around the circumference of the barrel, he put 9 bands of copper sheeting, spaced. And originally they had an aluminum chassis to the motor, and then they changed to some other material, plastic or something, I don't know. But then he changed back to aluminum, and then had Teflon coating put on the inside of the aluminum chassis. So he's got the aluminum brackets on the inside, then he's got the copper and, magnetic insulated copper wire surrounding those aluminum brackets. Then he's got the blowing compressed air acting as another stage of dielectric besides the insulation on the magnetic wiring of the coils. Now extended from that, he's got the compressed air, and then on the other side he's got the Teflon coating. So 3 layers of dielectric. 2 of them stationary, more or less. I mean, except for whatever. See, I'm not clear what rotated on the inside. Well, he had a set of stator coils and a set of rotor coils. So the stator coils were stationary, but the rotor coils moved. So he had some dielectrical material stationary and some moving. And then he had the aluminum chassis on the opposite side, on the outside, surrounded by 9 copper bands. And of course, that was stationary. So he was able to set up an electrostatic field, convert any of the magnetism that was that attracted the FCC in the first place, because just about all radio broadcast is electromagnetic. And they were putting out a very large electromagnetic field. So he converted that electromagnetism into electrostatics, in addition to whatever electrostatics he was already producing, and then blew it out by ionizing the air on the interior of the device, so that he could then eliminate or get rid of the electrostatic field also that was building up around his motor. But that was the last stage, or the penultimate stage, before he blew it out, which was the last stage. Okay. So those are 2 alternatives to getting rid of an electromagnetic and electrostatic field, is to convert it into electrostatics, reduce the electromagnetic, boost the electrostatic, and then blow it out with air, lots of air, that you ionize. So you create your own little ionization generator of sorts. Now we covered that. That was Mark McKay's analysis to the solution to the FCC problem. So we might have to do something similar here, because we're creating a humongous amount of energy that has no business. Whoops, wrong way. A humongous amount of volts and amps, a humongous amount of watts that has no business being in this motor because it's too much. There's no way we're going to be able to run a little electric car off of 4 megawatts. It's just not going to happen. So we got to get rid of all this energy, and I suspect we're going to have to do something similar. We're going to have to do what Richard Hackenberger did to get rid of the excess energy, because the coils on this thing are just not going to handle that. It's going to fry itself, and when you look at negative power, people who ask questions on, like, say, Quora or elsewhere about negative power factor, that's one of the, and various forums devoted to the topic, that's one of the prime concerns, is that you're going to get energy that's going to fry your device. Too much and excessive energy that's going to fry your device, because it wasn't rated for over unity. It was rated for under unity. So now let's see if we can produce. Okay, we want current only, and we want rotor number 2. See, if you do the current, the larger of the 2 first. So now the current is in blue, and normally I like to put the current in red and the voltage in blue, but we got to do it in reverse because the current is larger than the voltage. So now we can go back to the image or the schematic and just click on rotor number 2 to get the voltage in red. See how tiny it is? Now, let's look for the high, the peak. So the highest point of amperage, of current, is 6 kiloamps. Okay, so that's the peak current, not the RMS. And when we switch to voltage, the peak of voltage is 1.5 volts. So let's go back. That's 1.5. And what was the current? It was 6. So let's get our little handy-dandy calculator. Whoopsie, I don't want scientific, I want standard. So we take 6 and divide by 1.5. I tried to get one-to-one relationship as best I could, but I had a hard time doing it. The simulator was crapping out on me. It was giving me error messages on the one hand, transient time step too small, transient analysis time step, or it said the opposite problem. See, that's a convergent problem, but the opposite problem is it went to over unity and just blew itself up. Matrix is singular. That means the thing blew itself up with an excess of energy because the spark gap was failing to fire. So I had a hard time making sure the spark gap fired on the one hand and the simulator didn't crap out on me on the other hand. So the ratio here is 4 to 1. So ideally, in an electric car, what I see happening, at least in a DC car, no, in an AC too. Well, not Tesla motors. That's a whole different ballgame. But in the lesser priced sandwich spreads of electric cars, it's usually 1.67 to 1 of voltage to amps. That's the ratio, 1.67 to 1. Here I've got 4 to 1. And actually, in the Tesla Motors car, you have a preponderance of amperage, as I recall. I think it was over 1 kiloamps by some amount, and then the voltage was somewhere around 300 or 400 volts. So that's a different ratio, but it's not 4 to 1, and it's not volts to amps, it's amps to volts. Well, actually, this is amps to volts. So this is ideal. This is more closer to the Tesla Motors ideal than to the lower priced spreads. So that means you get a lot of acceleration in this motor, which is what the Tesla Motors car was designed to be. It was designed off of Tony Caccioni, what was his name? Anthony Caccioni. He designed the motor controller for the EV1, the General Motors EV1 from 1997 to 2003. And if you go see the movie Who Killed the Electric Car, he's in there. I forget his name exactly. And they interview him. So he was a race car enthusiast, but he was an electric car enthusiast. So all his race cars that he designed and raced were electric cars. And he started a company called AC Propulsions. And I can't remember if it's singular or plural propulsion. They're in, I don't know, Irvine or San Dimas, somewhere in Southern California. And so when the EV1, when General Motors crushed all the EV1s, and thus the movie Who Killed the Electric Car came into being, and a lot of unhappy people, because they never sold the car, they only leased it. He went and took his technology and donated it to Elon Musk. And Elon Musk made Alan, that's his name, Alan Caccioni, made him a silent partner. So you won't see him, you won't hear about him, but he's actually a silent partner because he's the whole reason why the Tesla Motors car has such good acceleration. Because he just took the motor controller out of the EV1 and put it in the Tesla Motors and racked up the price. Well, General Motors never gave us a price figure for the sale of the car, so we don't know what they would sell it at. But it really was designed like a race car. Just as Tom Hanks says on that little video clip of him being interviewed by David Letterman on the David Letterman late night show with David Letterman. Tom Hanks said, you get in that thing and it just zips down the highway and you can be afraid of getting a speeding ticket because the thing has such great acceleration. Well, yeah, because the amps dominate over the voltage. So that's where you get your speed. Whereas in Joseph Newman, you get all torque and no speed to speak of. You know, he hand starts it with his muscle-bound hands. No little old lady could do it. And then it does pick up a little bit of speed after the course of warming up. I don't know how long it takes to warm up, 15 minutes, half an hour. He never said in the Newman movie, the documentary, and so I don't know how long it takes. But he does indicate that it takes some time to warm up to speed. But it still cranks along at a relatively slow speed by comparison to electric cars, especially electric race cars. So that was my first order of business, was to try to fix that solution. And that's what I did yesterday. I created all these amps versus the volts, 4-to-1 amps over volts. But it's still negative power factor. So what we want to do now, I changed, you saw me, I put in a negative coupling coefficient in the transformer. So now we want to see if I succeeded in uniting the amps with the volts. I doubt it. I'm sure it'll still tell me that it's anyway, let's try and see what happens, because you know, whether or not we have to put in starter coils that have been rectified, and I've already covered that. I've done that in another circuit simulation, and I have to do it separately because of my limitation in not having paid the $4,500 to fully register my product. I don't get to make very complicated circuits, so I don't get to see the full implication of what I'm doing. So let's remove this upper bound and change it. Oh, my glasses are not functioning properly. Okay. So now we want to zoom in terms of time. So we get 7, if I can find the numbers, 7, 8, 7, and then the 9. I think 3 9s might do it. There we go. So now you see, we did not lose. They're still out of phase by 180 degrees. Let's go one down. See? So the red being the voltage and the blue being the the red being the voltage, right, and the blue being the amperage. They're totally 180 degrees out of phase, because if we select one of these, no, that won't do. All right, if we select one, we say that the peak of the amperage is totally lined up with the trough of the voltage. So they're totally still 180 degrees out of phase. So I didn't succeed. I didn't think it would. I didn't see any change in output when I changed the coupling coefficient, so I didn't think it was worth my time. But we still got to try, you know, to coil these in counter-winding condition. I know we'll have to here, possibly, the current coils versus the voltage coils will have to be counter-wound with reference to each other. But whether or not doing so over here will do any good, I don't know. It probably won't do any good on the two rotor coils, and they should be entwined together anyway, so they should probably not be messed with. So they're the only coils not to counterwind, I would imagine. I could be wrong. I could be wrong, though. See, I don't know. I can't simulate this, so I don't know. So let me see if I've covered everything. I guess that's it. So that's my update this morning. So you see the necessity of putting in an armature in this model. See, I didn't know that these coils did not have an iron core. I was dumb. These are air core coils. And so they build up a lot of voltage and torque. They build up a lot of electromotive force, a lot of torque. But there's no magnetomotive force to give us speed to speak of. So I had to boost the magnetomotive component of the fields within this thing, contributing to the magnetism and electrostatics. So those are 4 different things: electrostatics and magnetism versus the magnetomotive force and the electromotive force. Those are 4 different entities, and it's good to get it straight. They're not to confuse them. They're not the same thing, even though they're similarly related. similarly related. They are not the same thing. The magnetomotive force and the electromotive force are the proto-components, the proto-ingredients, or they are the ingredients or the components of proto-electricity. You know, they go to form electricity, but they are not electricity themselves. And then what we see when we measure electricity, the volts and the amps, or specifying the current level, that's merely the effect of their union, because we never see volts separate from amps, right? Ohm's law puts them together as a multiplicative relationship. We cannot separate them when we're dealing with electricity. But when we're dealing with the ingredients of electricity, now we're not dealing with Ohm's law anymore, and we're just dealing with two forces that are separate from each other and have not yet been united in a circuit. They're just floating around in the universe, you know. The magnetomotive force hanging out around matter, in close proximity to matter, so we get light in the atmosphere. We see the stars from the vantage point of Earth, but we cannot see stars from space because there's not enough matter in space to allow electromagnetic radiation of light to travel any great distance. It stops after a very short distance. And so all we can sense in the universe is electrostatics. And any kind of telescope, well, supposedly radio telescope, positioned in space would have to be an electrostatic radio telescope, not an electromagnetic variety. It could do the conversion. It can have an electromagnetic conversion inside itself to convert from electrostatics to electromagnetics in order to get the kind of images of light that we might want to see a star. But, you know, that's a conversion it has to do. Well, the atmosphere already does the conversion for us and then diffuses it, diffracts it, or both, diffracts it, but only after it's already done the conversion. So the aurora borealis, I would suspect, is the conversion process so intense that it lights up the sky in the north, and we call it northern lights. That's the actual conversion taking place between the electrostatic impinging, or exciting, I should say, the upper atmosphere of the North Pole area, and causing it to excite the atoms of air to produce all kinds of electromagnetic radiation that then gets transferred to surrounding air molecules and meets up with our eyes. So we're actually getting a mild current directly impinging our eyeball as a light wave. So that's what photons are. They're very, very weak currents that can only travel through matter at short-range distances. We're actually getting a slight current of excitement to our eyeball, to the retina of our eyeball, or else we wouldn't see this star, because if it were not for the atmosphere giving us that current. Without current, we don't see light. It's not going to happen. In space capsules and the helmet visors of space suits, they have Fresnel lenses specially designed to excite the glass to act as a as the right medium of excitement to the air inside the helmet to cause light to appear inside the helmet as a byproduct of the Fresnel lens on the visor. So the visor is a dielectric material, just like the vacuum of space is a dielectric, but the dielectric of space does not have a Fresnel lens embedded in it. That we have to provide on the space helmet visor, the glass visor. And then we have to put a layer of gold in there to prevent the poor astronaut from going blind if he should perhaps see the sun, even if only for an instant. He'll go blind, I think permanently. So they have to put a layer of gold in there, very thin. It's so thin you can't see it. The RAV4EV from between the years of I forget what year models. I know my model, the 2002, that's not operable at the moment, has a layer of, I I guess it's iron or some aluminum. I think it's aluminum. They put a very thin layer sandwiched in there, and they still continue to put it on the cockpits of jet airliners and jet planes. But it was too expensive, and it creates hazards. It makes it easy for the windshield to crack. So it was an experiment that Toyota did for the RAV4 EV conversion from the RAV4 gasoline engine into an EV model that I am now the third proud owner of, even though I can't drive it because all the batteries, well, most of the batteries are dead. And that's why I embarked upon this self-study course involving over 3 years of study at the benefit of simulators, various simulators, and various people like Eric Dollard helping me to understand what I was doing. And so I've gotten all of this expertise that's in my subconscious because I never took notes except for videos. And it's really a skill that I developed to be able to encourage a surge, nurture it into existence, and then try to manage it and hopefully get out of it something harnessable, something usable to put to good use. And negative power factor with a 180-degree separation between current and voltage is not exactly useful for a standard conventional motor. So it's a technical difficulty, a technical challenge how to put it to good use. But it definitely is free energy, and now it's balanced. I've got a magnetic component with lots of magnetomotive force surrounding an armature, and then I have the electromotive force associated with air core coils. And between the two, we may get both speed and torque for this thing to operate as a nice, hefty performance comparable to a Tesla Motors car. Yet the coefficient of performance between the output and the input, if I can find it here. Here it is. This input is 5.5 nanowatts compared to the output is 4 megawatts. So when you take 4 megawatts and divide by 5.5 nanowatts, you get 7.27 e to the 14 to 1 coefficients of performance. Do you know what that is? 7.27 e to the plus 14? That's 727 trillion to 1. Is that trillion? Right. Oh, it's 14. Well, let's see. Well, 12 is 4 groups of 3 zeros. So 100, million, thousand. No, 100,000, million, billion. And then the fifth group is trillion. That's right. 727 trillion to 1 coefficients of performance. So that's pretty good. Obviously, you would need a tiny little battery to power this sine wave generator. Actually, you would need a 12-volt battery. Yeah, you would need a 12-volt battery to power the sine wave generator. So you already have that under the hood. So you don't need a battery pack. And then you would use a group of solar panels on the roof of the car to produce the quantity of amperage to recharge the battery, because you're not spending a whole lot. You're spending less powering this car than you are probably powering the audio system in your car, because the audio system is usually not designed to be over unity, unless it was a John Bedini audio system. We're going to have to replace the audio system with a John Bedini audio system to be more economical. But anyway, be that as it may, because it had over unity elements in its circuitry, John Bedini admitted to, but he never told anybody. He didn't want to scare away the consumer. He wanted to make money. He wanted his brother Gary Bedini to make the money so he could spend it on his projects, such as the audio system that he developed. But to my mind, it looks like the power component of the car that's running the car is going to be spending less than the audio system. Let me tell you, it spends so little. I think that's everything. Oh, there was one little interesting thing. When I looked at the waves up close and did a measurement, let's see, where were they? They were at the warm-up stage. So you saw what I did when I zoomed in. I should change this. Yeah, this is not correct, this statement here. This is only correct in the beginning when this device first begins to start up. The frequency of the input current and the input voltage are different. The input voltage is set to 20 kilohertz, but the input current ends up being 95 kilohertz for some strange reason. But that's, I think, only in the beginning. No, that's not true. That's in the end. Oh, so this statement is correct. So yeah, no, I zoomed into this. That's right. Oh, this is the strangest thing. So let's bring up. Oh, I have to wait again. Yeah, the input current and voltage waves are not even the same wavelength. That's what's so bizarre. The current vibrates faster than the voltage for some strange reason. And that shows you that there's really no drainage. The current is free to vibrate at a faster rate, and it does so. And the fact that it vibrates at a faster rate shows that this thing is going to be stepping up its power, because normally when you see an increase of frequency, you're going to see an increase of overall power, because frequency is the predecessor. It's a potential form of energy. It's not kinetic, but it is potential energy, and it shows you that, oh, your kinetic energy is going to increase. So let's take a look at the voltage wave, and then let's add the current. Let's see, I got to get the current statement. Input, output. So let's see, voltage. Let's hope I get all the components here. Yep, that's it. Okay, now there's the current. You see how teeny it is in comparison to 3 volts? It's teeny. So now let's change the timing. First of all, let's make this 3. And then let's change the timing to 0.0739. That should do it. Nope. Okay. 2 9s. Okay. So you see the wave? Okay, the blue is the voltage, so it's dominating the current. But we don't get to see yet because we have to zoom in. So when we zoom in, we're going to lose. So remember now which way the wave is in this window of view. We've got the peaks over to the left side of the graph and the troughs over to the right. It's going to flip when we look at the red current. But we got to zoom in and remember the voltage because we're not going to see the voltage anymore. So let's see. How do I do this? Got to change the whole number. Let's see. No. It'd be, no, it would be well, let's see, 0. Start with 0. 0.001. And then let's do 0.001. See if that does the job. No, it does not. So let's add in 2 more zeros. That might do it. Nope. Okay, let's increase this to 7. And 7. There, we're starting to get... Okay. So, let's see, let's go to 8. Now how do we tell if this is shifted? Oh. Well, the fact is, the wave, the peaks are shifted to the right, and the troughs are shifted to the left. So we don't get, we don't get 2 waves to compare with. We get a multiple of waves. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We get we get about 4.5 times more because what did I say? 95 hertz versus 20. That would be a difference of about 4.5. 95 divided by 20. 4.75. So just under 5 to 1. Yeah, that's about right, because I counted 10 and the other was 2. But the peaks are shifted to the right, whereas before, the voltage, the peaks were shifted to the left and the troughs were shifted to the right. So it shows that it's still 180 degrees out of phase, but it also shows that it's a much faster frequency than before. So it's kind of interesting. You know, these are all interesting things you can do in microcap, is zoom in and whatnot. I don't make use of all the features because I don't even know what they are, and I don't try to find out what they are. Now notice that the capacitor here, the stabilizing influence on the spark gap, is 1e to the minus 9. That would be, I think, 1 nanofarad, if I'm not mistaken. But these other capacitors, the 3 of them, and they all end influence of stabilization, they're 1e to the negative 11, which means I think that would be 10 picofarads, if I'm not mistaken. So they're a little tinier. Now, I called this the throttle. Oh, that was the other. See, I knew there was something else. I had a thought this morning. And I think actually what we have to do... what was I was going to put another resistor someplace else. So this helps throttle the electrostatics, but we still have to throttle the speed, the electromagnetics. So we have to put a resistor somewhere, and I thought we can't take this out because it would destabilize it. We could put a resistor there in its place, but I think instead, maybe if we put a resistor in line, I wonder if it would louse up the simulation. Let's try that. Let's put a resistor here on the positive side and see what happens. I didn't try this yet, sorry.
Should have tried it before the video.
There's no room. Let's make it 1 ohm. And then let's move this out. Move this in. Move this up. Whoopsies. There. So let's simulate that. Oh, let's go back and change this because that didn't do anything. We'll take out the negative. Alright, now let's simulate this and see what happens. If it craps out on us, or... Because I had a hard time bringing down that 4-to-1 relationship. And I thought to myself, well, how are you going to change the speed on this? You got to have some way to regulate this. Now, previously, I had considered the possibility that you multi-strand this, and then you use little transistors, switches, to disconnect some of the parallel strands. But I never found good over unity from increasing this bifilar beyond trifilar. It was better on these current coils to make them multifilar. And I went as high as 8, I think was the maximum efficiency. If you add more, you don't gain a whole lot, but you would be able to regulate the current of these current coils, because this is there's no resistance here. The current just likes to flow around in this outer circle. All the resistance is in the middle here, building up voltage. And then because this is a step-down transformation, because it has a bifilar coupling of 99%, so you get a mass of current massing up here in this outer perimeter, and then all the voltage is amassing here in the middle. And then it blends when it transfers over to this rotor here. And then also then, because of 99% coupling, armature coupling, it transfers over to this rotor here. So let's see what is going on. with, let's see, what we want to take a look at. Well, we can't go there. Well, let's just take a look at the voltage, see if it went up. Oh no, it's the same. Huh. Alright, let's take a look at the, let's see. The current for rotor 2. Oh, it's the same. Nothing happened. It didn't bring it down. It didn't get in the way. I'm still getting over unity. Great, so it didn't change anything. So now let's increase the size of this resistor. Bring it out here. Let's just add in a kilo ohm of resistance to see what happens. And let's simulate that. See if it kills the over unity, or does it do its... my intention is to merely modify the over unity. Now we saw that the amps was greater than the volts, so now the volts should be greater than the amps on this rotor. So we should be able to increase... Oh, maybe I should put the resistor on this side. Oh, I may be putting it on the wrong side. That might be why nothing happened. Yeah, that's right. If I put it on the current side. Duh. Oops. Okay, I always... hey, I'm a newbie, you know. I always seem to do this. Whenever I do something new, I always do the opposite of what I should be doing. Alright, so what do we got? We got the same voltage. Yeah, nothing happens. I bet you that it's the same current, too. Yep. Humongous current. Okay. So let's move this. First we got to turn it around. And let's... oh, wait a minute. Let's take this wire out and put it over here. And then let's move this up. Move this into position. Move this back down. Whoops. And then lengthen this wire. Okay. Let's try that again. That should have an effect on changing the current to this thing. Isn't this fun? I love to simulate. You get to play around with these ideas and see what'll happen, so that when the real engineers go to design the thing, they know what to expect. 'Cause the idea man, me, went to the trouble of fooling around, having some fun for free at no one's expense but mine. Okay, so now the voltage should dominate. So let's see the voltage. It killed it. Probably changed the frequency. A little too severe. Okay, let's just do a mild resistance. Let's do the number 3. 3 ohms. Yeah, that should be reasonable, maybe. Well, we don't know that. What's reasonable? That was a little too severe. Okay. Oh, it's very severe. Wow, that's what I was afraid of. Okay, so let's change this to 1.1. 1.1 ohms. Because we're changing the frequency, not just the balance of volts to amps. That kind of sounds about right, that you're going to affect the frequency. Oh my God, is it severe? I want to see a little change. I want to be able to compare them. Okay, 1.01 ohms. Let's see what that does. So we're talking teensy-weensy throttling here. Ah, this is a little better. Yeah. All right. Ugh. Wow. Well, you know, you have two resistors that are in parallel. Your main resistor is 1 ohm, and then your tiny little resistors. Well, actually, no. You would have... oh, that's right. You would just have a lot of 1 ohm resistors in parallel. If you can't get a high voltage or a high current resistor to be less than 1 ohm, then you just add a lot of them in parallel to divide up the current, such as I'm doing here. 1.001, so that's 1 ohm plus 1 milliohm. So I added a milliohm to the 1 ohm because I'm having a hard time making a tiny change in the current. Well, because 2 micro ohm coil, I have set to 6 micro ohms of resistance. So you see, anything greater than 6 micro ohms is going to make a drastic change. Oh my God. What did I say? Anything over 6 micro ohms? Yep. Yep. So now this is 100, no. 10, wait a minute, 100? No, wait. 0.1 would be 100 milliohms, 10 milliohms, 1 milliohm. So this should be 100 microohms. So we added 100 microohms of resistance to the 1 ohm. It might still be too much. Yep, it's too much. Yep, this, oh my God. So now I got 10 microohms added. Maybe we have to add just 1 microohm. Who knows? Who knows? Oops, see? I was right. Oh, I'm not getting any benefit. Oh my God. Well, I had no problem with 1 ohm. Didn't I? Oh, I never did try 1 ohm, did I? Well. Alright, so let's try 100 milliohms. Whoopsies. This is okay. This is not like Paul Falstad's simulator where capital M means mega. Here you have to write out MEG for mega, but just for clarity's sake, let's make that lowercase m for 100 milliohms. So actually, you have to add in teensy weensy, because I had it on the wrong side. I had it on the voltage side, and nothing was happening. So now everything is happening. Oh my God, it's so delicate. Oh, this is more like it. It's taking longer now. Now we're going to get our waves. So it should work. It should. So this is the throttle, the actual throttle. So this is the power throttle. I should call this power throttle. I'm going to rename this power throttle. No, the torque throttle. No, this is the boost. I should just say R1 because it's not the throttle. And then I'll rename this resistor the throttle, the actual throttle, because that's the way I think, that's the way it should be. Ah, see? So it took longer. You remember before it warmed up and started the staccato wedge surges at a much earlier point in time, somewhere around over here. So now it took longer to warm up, and the peaks are below 200 volts. Instead of the 1.6 was the limit before. So we've reduced the voltage. But now let's see what we've done to the current. If I'm going to have to go back the other way. Oh, so it's still, the amps are still greater than the volts, but the overall wattage has been diminished. And I think that's what they do in an AC motor. They call it field excitation. They vary the field excitation of the coils, which means you know, in a DC motor you vary the current and you keep the voltage constant. But in an AC motor it's a little different. So I guess maybe that's what I've managed to do here. I've managed to reduce the excitation level overall of the coil because the amps still dominate, but they don't dominate as much though. They have come down. That's right, they have come down. So let's see, if we look at the peak voltage is 163.9.5. Let's just say, well, yeah, 163.9.5. So let's get the calculator. 163 0.948 divided by, that was the volts. Now the amps, 245.287. 245.287. So we've got about a 2/3 relationship. So the voltage is 2/3 of the amperage. And otherwise, turn that around, it's 1.5 to 1. So the amps is 1.5 is 3. It's 3 to 2. So it's the relationship now is not 4 to 1 anymore. Now it's 3 to 2 amps to volts. So we brought down the ratio, and I bet if we brought it down some more, it would continue to suppress the amps, and before you knew it, the volts would dominate over the amps. But overall, the wattage would be diminishing as well. And I guess that's what you want when you want to throttle. You want to bring down your overall power, but you also want to bring down your amperage to voltage ratio to reflect the fact that just because you're running an AC motor, an AC system, doesn't mean the DC is not there. Remember, every half cycle it's DC. It's the change between each half cycle of an AC cycle that makes it AC. The current reverses direction, but, well, the voltage reverses direction as well. Everything reverses direction. But during the duration of each half cycle, it's DC. That's why it's called alternating current, because it alternates. But the alternation only happens between each half cycle, not during the half cycle. So it's something to keep in mind here, You get the ramification of AC only in the change between each two halves of the cycle. Otherwise, strictly speaking, during each half cycle, it's DC in how it behaves. Now, it may be reacting still during the course of that half cycle to the change that happened at the beginning of each half cycle, but that's a different matter. The point is, the current is behaving as DC during the half cycle. And so you have to look at it both ways when you do an analysis. You have to look at it both as an AC point of reference as well as a DC analysis in order to get the full benefit of what you're trying to study. It's good to point that out. Now I think I've covered everything. So I got a throttle now, which I didn't have before, a truth throttle, and this was simply a regulator to deal with all of these other components. So this is not a true throttle. It's not something you can dynamically change. It's set, so it's not the throttle anymore. I thought it might be, because it did change things, but in a complicated way. You have to change other things as a consequence to changing this thing. And this really is the power section of the circuit. And this is what we want, the speed. So this will provide the torque, and this will blend the torque with speed as it converts the torque into speed. It'll blend them. All in this armature here, the motor armature. Okay, so now I got to change this to throttle. So let's do that. Let's copy this and then change it to R1. So now that's R1, and this becomes the throttle. And something along the lines of tens of milliohms of resistance modification to this, dynamic throttling action of this resistor here. Something along those lines, I don't know. Let's just, ballpark figure, let's just say tens. Now I call this rotor 2 for a reason, because this is the secondary of the bifilar pair. This is the primary. This receives the energy from here, and then it gets transferred to number 2, rotor number 2, and then in turn then gets transferred to the motor armature of, I guess this would be the rotor coil here. You know, these 3 coils would be the rotor coils, and then this coil here is the stator coil of 10 henries. So I should say that. I should put names here for these 2 coils so that we understand what they are. So this is really in combination it should be rotor 3. This 200 nanohenry should be rotor number 3. And then this coil down here should be the stator coil, is what it should be. And this is the motor armature. So now that we got that all straightened out, one other thing before I go. The Arthur Matthews version of the Tesla Pierce Arrow story puts the Pierce Arrow demonstration not in 1930s, but in 1897. And Peter Savo probably wasn't even born yet, because he was young. He was a young assistant, and he was not the nephew to Nikola Tesla. But he was also a thief, and Tesla knew it. So that's why I think what happened was Tesla told him a fairy tale story of what he did. And maybe, I had an uncle who would tell me stories, and he would put it in the name of my birth name and say, David and the white Pegasus, the white horse Pegasus with wings. And, oh, is it the same David as me? No, there's a different David. So, and this is what I think the Book of Esther is, because a rabbi told us that all rabbis agree the Book of Esther is a work of fiction. It never happened. But I suspect the author of that fiction put himself in the story, namely the father of Esther, I forget his, Mordecai. Mordecai was an actual person, because my inner knowing is that I met the reincarnation of Mordecai. He was a neighbor, she, in this incarnate life, one of my neighbors when I used to live in Studio City in the San Fernando Valley of Los Angeles. So I suspect, it was like the Alice in Wonderland story. The guy who wrote it, Lewis Carroll, he would tell these fantasies to little Alice, a real live person by the name of Alice, and put her in the story and kept himself out. Well, in the case of Mordecai, he put himself in the story, and it might have been a bedtime story that he told his daughter Esther, and put her in the story as well. Put both of them in the story, so that she could enjoy the fantasy, that they were both in this fantasy together. But I think something like that might have happened, because Peter Savo then went and spread it around as if it actually happened. And of course we know it couldn't have, especially as a radio reception. No way. No way. It's a work of fiction of probably Nikola Tesla, making up a fictional story, telling it to Peter Savo, and Peter Savo just ran with it and told it to us because he doesn't know any better. He doesn't know any differently. But he's not a credible witness because he's not a nephew, and he's not a credible witness because he wasn't there when it happened. According to Arthur Matthews, who was an assistant, it happened more than 30 years prior to the Peter Savo version of the story. And it had nothing to do, it was an 18,000 RPM. Am I right? Oh my God, 18,000. Holy moly. This is 20 kilohertz per second. That was, no. Yeah. Oh my God. This story was 18,000 RPM. Oh, I gotta verify that. I'm sorry, I gotta verify this. This sounds ludicrous. But the story went on to say that he used hydraulic transmission to tone it down so that his wheels could turn. So you see, I didn't make that up. I actually got that idea from the Arthur Matthews story. I just forgot that I got it from that story. Where are we here? Here we go. No. Here. Here. No. I don't have a recent... Okay, I don't have a recent... Okay, so let's go get this recent version here. I hope it works. So, I did some changes to my website, Tesla Pierce Arrow 1931.info. Is that the name of the website? Yeah, I think so. Wait a minute. Tesla Pierce Arrow 1931.info, right. I made some changes. I took out a lot of the simulations, not all of them. So I tell you about read the ebook, and then I talk about the Arthur Matthews story. And this is the quote that I got from newenergy.org, is it? Yeah, New Energy, NU, the letters N is in Nancy, U is in Underwood, nuenergy.org. And let's see, where does it say the RPM? 1897. Oh, maybe we can increase this. I can't see worth a dime here without my glasses. Ah, there we go. So, 1897, he drove from New York City to Buffalo at 94 miles an hour. And he had a zinc battery, a primary battery. He would swap out the plates, the zinc plates, 500 miles before the plates would have to be changed. Where's the frequency? 30,000 RPM, excuse me. So it's 30,000 RPM. So we get our handy dandy calculator. 30,000 divided by 60. Oh, it's a mere 500 hertz. Oh, that's not bad. Oh, so it's nowhere near mine. I don't know where I got 18,000 from. Well, 18 was half of 30. Yeah, whatever. So this is the story that is probably more fact than fiction. And I have to say, that's the way things are, Okay, no, I was playing around with an oscillating Earth battery. That's one of Paul Falstad's. Oh yeah, I had a picture here, but apparently the picture doesn't come up because I'm not connected to the internet. So anyway, where do I get this back to regular size? Oh, I don't see it. Okay, so I think I covered everything. So I guess now you know the latest and the greatest of what I've been working on, and I have to make some now further changes to my ebook. I made some yesterday, which was July 17th, but now the 18th of July 2019, I got to make some further changes. What I described in this video, I got to add it to the text and change the schematic. And by the way, you can download the schematic. I don't have a shortcut URL. I should make a shortcut URL. You can download the compositional image, Heaviside Ferranti. I'm going to have to add something. So let's make the schematic Heaviside Ferranti schematic. Yeah, 3 words. Hardly a shortcut, but at least it's easy to remember. Heaviside Ferranti schematic, and that'll be the microcap simulation file. Is that the way I want to do it? Well, yeah, duh. This is a composition. I don't call this a schematic. Yeah. Whatever. Yeah, schematic. Sounds good. Okay, until we meet again. Happy trails to you. Until we meet again. Happy trails. I'm a Roy Rogers fan. I love that program. Roy Rogers and Dale Evans. They were such nice people.